Good morning, ladies and gentlemen. I am Kitagawa with Kyoto University. I am at Institute for Integrated Soil Material Sciences of this university, which is a short name as ICMS. This is the title of my talk about such a material with such a skeletal structure. I have three parts as I go along. Part one is about our world, where we live. Second is how my science has developed, what is the background. And the third is what those materials can do. Now, in the 19th century, we saw Industrial Revolution in the United Kingdom. We came to consume a lot of energy from that time on, and we have built such a social structure of consuming enormous amount of energy. And we first used coal as a resource for fuel. In the 20th century, it was replaced by petroleum largely. What about the 21st century? That's gas, such as natural gas. What does it mean? Solids. It can be left there as they are, but for liquid, we need a container to store. What about gas? We need a more precise and more strong container. So the technology has moved on from something simple to more complicated and difficult to handle. However, coal and natural gas or petroleum will no longer be there. It has certain limit, but we have a lot of gases around us. This shows the population over years, and advanced countries are shown in purple and developing countries in yellow, and we are here. Now advanced countries' population remain more or less the same, but the population is increasing in the developing world. Several decades ago, advanced countries began to consume a lot of energy, resources, food and water. We were almost monopolizing all of those resources. However, it's now very difficult to share those resources. Each nation is exerting their nationalism to have a larger share of such natural resources. Now, according to this paper, the population in the near future, 2100, is going to be 12.3 billion. And more recently, the United Nations did the same kind of analysis. In 2050, that will be 9.8 billion, and the 2100, again, over 10 billion. So population is increasing enormously. Then what can we do about this? Here you can see hydrogen, oxygen, all of those more or less a simple molecule made up of a few atoms. In usual circumstances, other than water, they are in the gas phase, and they all contain the atoms elements we are necessary: environment, natural resources, energy, and for human life. All of those elements are essential for all of those aspects. This is the SDG, Sustainable Development Goal by United Nations toward 2030. There are 17 goals: food, health, water, energy, industrial innovations, or rather industrial promotion and sustainability, climate, and water. From ocean and rivers and life on our land. All of those are related to science and engineering. Otherwise, we are not able to resolve the issues. And also chemistry, my field, is essential to solve those problems. Now, petroleum has been producing so many useful things around us, energy as well. They have been indispensable for us, but what happens when we have no petroleum any longer? Then we might have to use more ubiquitous resources to replace petroleum as a resource for products. they are ubiquitous, so there is no competition for them in a nationalistic way. But actually, those gases can be easily mixed and diffused and very low in concentration and invisible, very hard to handle. In order to use them more effectively, we need porous materials. By so doing, we are able to operate those gases under mild conditions, low energy, room temperature, low pressure, and low concentration. Then how can we handle gases? First, we need to separate them and then store and convert to useful materials. All three functions are necessary for us to use the gases for our society effectively and usefully. Now about the porous materials, looking back, actually 2,500 years ago, it was already used in papyrus, for instance, for medical applications and purification, according to the papyrus. So porous materials had such a long history and had been useful for human life. And in the 18th century, zeolite was discovered, and further advancement was made in zeolite, which is inorganic, which made a great advancement in the field of petrochemical industry. But in order to resolve the issues I mentioned earlier, they are not enough. So we have to be able to find a technology to operate those materials with a low energy, and we need a porous material to recognize, to capture, to separate, store, and condense them. And we discovered the ones I showed you, such as MOF and PCPs 20 years ago. Now, porous. In our history, can we find such a Chinese character? Actually, 2,000 years ago already in China, a concept of pore and that Chinese character were in existence. So it was actually activated carbon, but our concept was already there about pores, and we already had a Chinese character for porous materials. So porous materials have always been around us. Then what about this chemistry of small spaces found in porous materials? When I was a student, I read the Chuanzi, and I was impressed by this particular passage. All people, everyone knows the usefulness of the useful, but no one knows the usefulness of the useless. But actually, there is a utility of the useless. Already in the 4th centuries BC, there was such a great philosopher who gave us such an important insight. And in Kyoto University, we are encouraged to do something other people don't do. So I think that is actually a challenge I have been taking on. Look at this image, two men facing each other, but from a totally different angle. We can also envision such a vase. Again, this shows the utility of the space. So nothingness, yes, nothing, empty. However, even for a small spore, iron molecules can be utilized and can be given a certain function in such a space. And this gives rise to a new chemistry. By separating a space by something, we can give a function interior to this small space. And exactly that's what we have been doing as a material scientist. Thus, we are trying to make many kinds of spaces. It could be legal or any other word. It's like using various building blocks. Then, as a challenge, we have so many different structures around us in a macroscopic world, but can we replicate them in a sense in a nanoscopic world? In nanoscopic world, which we can handle on our hands, what can be done? But before that, let's look at our world, macroscopic world. Pillar layered structure can be found with the Parthenon and Angkor Wat, historical buildings which are still in existence today. What about on a nanometer scale? Do we find anything similar? Here, ions and molecules can be stored. Can we make such a nano structure? This is what we made, a copper, metallic ion, and organic molecule. I will not use any technical jargon. Those molecules and ions can be used to make such a pillar layered structure. And this is a kagome basket lattice. Can we make such a structure on a nanoscale using those materials? We can make such a green crystals, and actually they have such a kagome lattice structure. This is a rock salt structure, easy to understand, and they can also be made on a nanoscale, and also by changing the size of the unit we can make them larger. And this is diamond structure. Carbon atoms are connected in such a way. Can we make this by using metallic ions and organic molecules? We can once again make such a structure. What about honeycomb structure? Yes, this is something we also made. A copper ion and those organic molecules are linked together for making such a orderly structure. So we can design molecules, and we can design even a structure on a nanoscale. So this has been a challenge, but we can make it a reality, and we can produce something on a nanoscale according to our designs.
So can we actually make it, this is a rock salt structure. This is what you want to make. What you imagine your brain, and see it is painstaking. But in the nanoscale, you need infinite time in order to make something as big as visible to our eyes. So I throw out components, then it's made automatically. Is there a mechanism that enable this kind of making? Yes. The key is the use of coordination bond. Metallic ions and the organic the molecules are connected as if we are using glue to get 3D structure. And we call it metal complex. Then using this, according to the design, the metallic ions and the organic molecules get connected based on the information given according to the design. It's not done spontaneously. We give design to those components, and the metallic ions and the organic compounds make nanoscale connection for bonding. As we make it larger, we can make it to the macro scale, and now we can call it a crystal. But this crystal, the micrometer size, not visible to our eyes, but if you have the lens, you can see it. But what is the situation, the micrometer level crystal? 1 micrometer. By using our method, we can clearly show you the structure we can make. This is very orderly arranged. 1 micrometer. There are 1,000 because each size of the pore is 1 nanometer. So, and 1,000 by 1,000 means 1 million channels. In a completely orderly manner. And when molecules come in, this is CO2s. This is what we are coding the PCP porous coordination polymers or metal organic frameworks. Designing metal ions, organic ligands, we can create structures according to our design. To make it easier for you to understand, I would like to talk about the benefits of the small nanometer size pores. There are the 4 panels of 1 square centimeters, and the surface area is 4 square centimeters. 1 micrometer channel, we can get 400 square centimeters. What about 0.8 by 0.8 square nanometers? Then the surface area is 200 square meters. Square meters, not centimeters. Why 0.8 by 0.8? Methane 4 of them can be contained in the pore because the size of each methane is 0.4 nanometer. So we can get 150 the cubic centimeters. Isn't it like a kind of hotel which can accommodate so many guests every night? Zeolite, activated carbon. Zeolite would have the surface area of 500 square meters per gram, like a basketball court. A carbon material is about half, but we can get a surface area that can cover the football or a stadium completely. And what is the effect of the small pores? This interaction may be weak, and if you have 2, this is a sandbag, but if you have 4 plates, you can trap the molecule quite easily. But can we synthesize them quite easily? These are the solution of the metal ions, and this is the organic ligand solution. You put it. This is a real time, not a fast the one, and you already made it. And then you need to filtrate, and that's all. Yesterday, the experts on the humanities, even they can make it. And you would not need scientists like us because making it is so easy. Easier way is to use the motor for grinding for 10 minutes. It may be too hard for your hand, then you can use the metal ball for shaking. MOF Technology is a company which discloses this technique. We also use the same methodology. A short time shaking would be same as grinding with a motor. Or microwave, since this is possible, you need only 1 minute. Or the interesting way is the spraying. Spraying metal ion organic ligand alternatively on a or you can get the shining crystals. Because it's so easy to synthesize, we have more than 7,000 reports per year. So it's a very competitive field. But are they stable? Think about the macro scale. You may think that the stone is very sturdy, organic is okay. The wooden, it may be okay, but what about paper? Cardboard houses should be very unstable. But this is only in the macro scale. Inorganic and art level. If we take in and out CO2 for 600,000 times, there would be no changes to the performance. They are heat, water, acid, alkaline resistance. So they are very stable.
Then functions do they have? Separation, storage, and conversion. What about storage? A function of storing. Such a material is made of a lot of pores, made of metallic ions and organic molecules. This cylinder contains our material, MOF, and the other doesn't. Then we introduce CO2s in these 2 cylinders, the same pressure, 5 bar. Those small cylinders, this one doesn't have a porous material, and the other one has, and under the same pressure. Then we open up and try to open up this to achieve atomic pressure. When we open this one up, this is now reading 1 bar, and this goes to this balloon. Only that much. What about this one, which includes the absorbent, our porous material? Again, gradually the pressure comes down, and gas is introduced into a balloon. Of course, it depends upon this equipment performance, but in comparison to the control, you are able to compress the gas a great deal. Then what about CO2? 10 years ago, already at 5 bar with 1 gram, over 6% of CO2 can be stored. At the 50 bar, 70% of CO2 can be obtained in a certain material. Suppose that there are empty cylinders, and this material can store CO2 9 times that of contained in 9 cylinders. So in terms of storage, this material has the best potential for storing. Now what about methane? 20 years ago, a nationwide newspaper released this data, methane distribution in atmosphere. Red indicates the higher concentration of methane, which is a greenhouse gas, but it also is a fuel for us. Over Japan, not high concentration, but in Europe, in Middle East, in North America, methane concentration in the atmosphere is high. And in order to have an onboard methane cylinder on a vehicle, 235 square centimeters is required to drive a car between Tokyo and Osaka. But we have better material today for storing a methane, and the BASF, a German company, is already realizing such a cylinder on board. And we decided to look at a more dangerous gas such as acetylene. Acetylene can be a source of many materials and things, and this one exploded. A serious accident indeed. And thus the car is completely destroyed by this explosion. However, using our material, we were able to handle this acetylene more easily. Usually acetylene, which is useful industrially, explodes at the 2 bar under room temperature. This is the pill layer structure we used to store acetylene more safely. That is the crystal. This is pressure by amount absorbed. The structure is very similar between acetylene and CO2, but only CO2 acetylene can be absorbed because of this structure. As you can see at the cross section of the pore, there are double hydrogen bond. The hydrogen bond which can be seen in the water. So double hydrogen bond was used to pin down acetylene. So because of this bonding, they cannot react so easily. As a result, we are able to achieve the concentration 200 times the lower explosion limit of acetylene. When they come near, they tend to explode. So under the pressure, they get closer, and that happens at only 2 bar. So pure storage of acetylene couldn't be achieved when that is beyond the 2 bar. However, in the case of porous material, acetylene can be stored in such a very orderly manner. So be it such a dangerous gas, we are able to store them more safely in such a porous material. This is made by a Northeastern group. This is their startup company, spin-out company. In electronics industry, such a dopant gas, the dangerous gas is necessary. Silane or arsenic gas, and they have a technology to store them in large amount in a very safe manner. It's already in the marketplace. Other than those examples, there are so many startup companies who are making such porous materials. They are very easy to produce, as a matter of fact. That's why there are so many spin-out companies today. Now, what about separation? This shows the energy consumption breakdown of different industries in Japan. Chemical industry account for 34% of energy consumed in Japan, and 40% of it is spent on some sort of distillation or separation in a sense. So that means 12% of all the energy consumed by industry in Japan is spent on separation. And this is important comment from Nature recently. That is, Around the world, operations such as separation distillation account for 10 to 15% of the global energy consumption, exactly the same level as we find in Japan. And if this problem is resolved, then in the case of United States, they can save 100 million tons of CO2 and $44 billion energy saving. And all of those are about gases. And so gas separation is indeed a very important issue for us to resolve. So we decided to take on this difficult challenge. Those indicate the size and the boiling point of different gases. Size means the size, and also and the boiling point means the interaction. CO2 and methane, those are the components of natural gases. They are far apart. They have different size and different boiling points, and they are easy to separate. Acetylene and CO2 that I mentioned earlier, and ethylene and xenon and argon and oxygen and CO and nitrogen, they are very similar to each other and really difficult to separate them. It requires enormous amount of energy to do so. But if you look at the mixture of gases, they are coming out of the chimneys, and also in air, we might want to separate oxygen out of air. So there are so many gas separation operations we would like to perform more easily, effectively around the world.
This is a conventional guideline. We looked at the size and the shape. If the pores are too large, it cannot be recognized. If it gets smaller, the interaction with the target occurs. This is a conventional way of thinking. Looking back at the history, activated carbon has many different size of pores, so that's why it was widely used. And the zeolite has more regular size of the pore, and it may fit certain targets but not others. Now we need to develop new kinds of porous material. What is it? The issue is, or key is that it can respond to the target gas molecules using the metallic ion and organic the molecules. This is our material, meaning so size can also be changed according to the target. And this is what we call the soft porous crystal. This is a crystal, but it also works like a sponge. And something quite interesting can be achieved. We have myoglobin in the muscle for the storage of the oxygen. Hemoglobin is there to transport. And myoglobin is made up only one molecule of protein. This is how the oxygen is applied with pressure. And the hemoglobin is tetramer. There is interaction among four of them, four proteins. Once the incorporation starts, it is the adsorption accelerate. This is what we can do. This is a good hint. This is a toy. As you can see, the whole changes its shape, but no changes to the components, only the changes in the angles. So what we want to do is to do it in the nanoscale. Different ideas are possible. Stacked layers with mutual or the dislocation gives you softness. With hinge, you can make it flexible. Or the interpenetration may also be a way to achieve mutual dislocation. And this is one of the things we developed. This is interdigitated structure. By opening it, you can create spaces. What could we do with this material? At the room temperature, CO2, CH2, or O2, and N2, at a different pressure, we could open gates differently. By applying pressure, a gate open for a certain type of gas. At the different level of the pressure, when it's lower, the gate closes. So with pressure, it expands. The most difficult material is carbon monoxide, CO. And there is a carbon inside. And carbon is a very useful material for anything that we could use. But the CO, once it's exhausted into air, it's impossible to be separated from nitrogen from the air, but it has many use if we can separate it. What about activated carbon with the pressure? And CO and N2 would have the same level of absorption. So it's impossible to separate between the two gases. And our material with Kagome structure, we wanted to separate these two different gases. And this comes as a very beautiful green crystal using the copper and the organic molecules. Then you can see that the N2 absorption, but the absorption of CO dramatically increased with the pressure. Why is it? We analyzed the mechanism, and I will show you the essence of the mechanism with a movie. These are the channels in the structure. This is a copper ion, and CO is bonding, and N2 cannot, nitrogen cannot bond. And when there is a bonding with a CO, then the next gate opens, and this CO comes into the next space. This one is already crowded, and N2 even cannot come in. Only CO is allowed to come in. So this is a way to accelerate the absorption of CO. So this material only recognizes CO but does not recognize nitrogen. Starting with 13% of concentration CO in a mixed gas, after 3 repeats, the concentration increased more than 95%. Storage and the separation are now possible. But what about conversion? We need work more for conversion. But what is the future that can use more effectively conversion? This is by Dr. Ola, and he wrote a book titled The Methanol Economy. CO2 in the atmosphere can be taken in using the hydrogen from the water, and renewable methanol can be generated. And the methanol are the basis for various fuels and chemicals. Once they are burned, they go back to the atmosphere. But by repeating the same process, you can capture the material again. So this is a dreamlike society in the future. And biogas has the concentration of CO2 50%, but it's only 400 ppm in terms of CO2 concentration. But by using the porous material, we would enable direct capture and separation of CO2s. And the catalysts are widely developed, and by joining them with the catalyst, we can realize direct capture and separation. If it becomes possible, currently we use petroleum and coal as a raw material for the synthesis of the petrochemical. By switching to the natural gas system, separation, storage, and conversion will enable the use the ubiquitous resources without changing the upstream. In the future, we will be able to use even the air and the biogas as resources, and that would make contribution to the peace. Because today, the nationalism is the causes of conflict because the resources are limited. But the air is limitless. You can find water anywhere, and air and water can be resources for the new kind of society. But to make it happen, for the separation and storage, and also for the conversion by using the catalyst, integration is necessary. In order to use energy effectively and convert it using catalyst, and the hydrogen will be generated or taken out. Integration of different functions should be possible by designing innovative materials in the future. This is my dream, using the porous materials in nano-size. Then we can put it in our body. Then materials would generate the reaction to turn toxic material to intoxic, or the amine are very bad for the liver. And by putting these materials in the body, we would have a mechanism to turn the toxic material into the useful materials. I've talked about the science technology of gases, environment, energy, and natural resources. I did not have time to talk about the impact of gases on life, but we will be able to handle different aspects freely. This is a kind of chemistry we would like to develop to make it happen. We want to utilize engineering to give new perspective to our future. I work at the Kyoto University Institute, and we are developing advanced porous material to make a contribution to the society. And we are studying at ISEMS. Please visit our homepage if you feel interested. What are the objectives for a scientist or researcher? Scientists, you may think that we live in a silo, but we are working toward the free discovery. Discovery can be done by everybody, because you can enjoy making a discovery, but you want to make a discovery that can affect not only your field but other fields. You are going to have a sense of wonder. But if you want to make a benefit to the wider society, then you feel passion. Discovery, wonder, and passion are the direction of our researches. So you may think that the mountain immortal wizard live on air and moisture vapor. And usually you talk about those mountain wizards as an example of something impossible. But the air and the moisture vapors and the carbon and oxygen and the nitrogen are all included in the air and the moisture vapor in the atmosphere. So we have material for the food and the fuel. So it may become possible to live on the fog because it contains all the necessary elements if we have the capability to use it by way of innovative porous material that we are developing. Thank you very much for your kind attention.